So, okay, before we start, first I'm going to give you a kind of an overview talk of the capabilities of Sirius and what we are doing today, because this talk is now all about compound annotation. So the other already introduced you to feature finding, to statistics, and Sirius is really focusing on now to annotate your features that you're interested in. But before we start, if you haven't so far, first of all, download the Sirius software, because in the hands-on, we are going to use it. And also, we have some data in the drive that we shared for Sirius. And if you haven't downloaded, we will need basically this file here, the custom structure databases. This is very small. This is downloaded quite swiftly. And then we will need some data. Basically, I pre-processed already some of the MC-MINE export. And so for the hands-on, we are using this one in this folder because some days ago, Steffen still reprocessed with MC-MINE. So for the rest of your workshop, when you are doing all of the integration with the tools in Cytoscape, you can just use the data in here. But I think Daniel will guide you through this. And for the workshop, we will use in this folder, basically here is the pre-processed data, which you can just download it and then have a look in Sirius in the hands-on part. So, and this may take a minute, or just start downloading now, then we are good to go at the hands-on. So this is all the data we look at, and if it's too slow for download, just use the upper file. That's like the minimum we need, and the MGF, and then we can also play with that. So, okay. What's with the green lines here? Is it also in the streaming, or is it only on this? Oh, on the screen. Yeah. Yeah, some artifacts, right? Some kind of, yeah. Is it probably nothing I can change? Let's keep it that way. I don't know what the issue is. So yes, Sirius is all about compound annotation. So what we provide you with is if you have your features, a single feature or a whole compound list, a whole data set, we can perform annotation of molecular formula. We can give you a structure. And sometimes if we can't give you the structure of your hit, we can at least give you some compound classes to give you an idea. So basically all of this is performed in Sirius. And maybe to give some differentiation to other levels is maybe not a good word for it, but other approaches, how you can annotate your features in your data, what the advantages and disadvantages are. I mean, you can already annotate compounds in your dataset with MS1 only if you're really knowing what you're looking for example. I mean, if you're really going to targeted approach with MS1 and you have a retention time, you may go without tandem mass spectra, but this is only for a handful of things what you already expect to find in the data. So that's not really what we are aiming at, right? We want to find compounds where we don't know in advance that they are in our data set. We don't want to rediscover them. And the usual way to do it is spectral library search. So you can search your tandem mass spectra in a spectral library and you get some hits and you're good to go. And the good thing about this, for example, is it's already independent of your setup. If you look for MZ and retention time, you can only do it on your machine, basically with your setup. But this you can do now with GPS and you get your hits. But you still need some measurement, some of your reference measurements of your data, basically. So what we are aiming at is, for one thing, performing structure database search. So we we don't need to have any reference measurement of the compound you're looking for. If it's in a structure database, we can find it. So this gives you a couple of advantages because it's still independent of your setup, and it gives you 2D structure annotation, but you can now find much more because you are not required to have this reference measurement. And what we can also do is we can use like custom structure databases. So if you just have a structure in mind and you can draw it on a piece of paper, we can basically try to search it because we just need a structure representation, and that's the way we go. And then I was talking about compound class prediction. So we can predict, is something a flavonoid? Is it a glucoside? This doesn't give you a full structure, but it has the big advantage that it's completely database free. So if you are looking for completely novel molecules, then basically you can still get valuable information by getting compound classes and not having it in a database. So the point I'm trying to make really is this big advantage if you can search in a structure database compared to spectral libraries, because structure databases are just orders of magnitudes larger compared to your spectral reference libraries. And they will always be, because we will never have millions of reference spectra out there, but we have structure databases with millions of structures in there. Yeah, and so Sirius is now this complete suite where you have different tools in there which can perform for you molecular formula annotation, structure database search, compound class prediction. And I will now guide you through all of these different steps and always focus on the task at hand. So let's start with molecular formula annotation. This is, for historical reasons, this method is also called Sirius. So we give basically every of our methods a name, because after 5 years of development, we just grow fond of them, and for the paper, it needs to have a name. And so initially, the first method was Sirius for molecular formula annotation. So this was also where all the software started. Initially, it was always meant to be a software for molecular formula annotation. And so it sometimes can be a little bit confusing, but basically the software where everything is in there and the method for molecular formula annotation, they're both called Sirius. But enough about that. So how do you do molecular formula annotation if you know nothing about a compound? You know that if you have a molecular formula given, then it's easy just to calculate the mass of the molecular formula, right? But it's also possible just to go the other way around. If you have a given precursor mass, you can just generate all possible molecular formulas that match this mass. This can be for low masses, that can be just a few, but for large masses, you can get like 10,000s of molecular formula candidates. So now you need to have some way of deciding which is now the correct molecular formula for my measured compound. And what we can do is, the two kind of data we have is, on the one hand, the MS1 data, and on the other hand, the MS2 data. And we can use the MS1 data to score molecular formulas by just simulating isotope patterns. So you have a measured isotope pattern in your data, and for a given molecular formula, we can just simulate how an isotope pattern should look for this molecular formula. And then we just compare, and if they match well, they have a high score, and it's hopefully your correct molecular formula. And on the other hand, we have all this information from the MS-MS data. And we can also use this for scoring. And for this, we introduced the concept of fragmentation trees. And to guide you through what fragmentation trees are doing, basically, like I said, you start with the MS2 and the precursor mass. And now you can, based on the precursor mass, just generate molecular formula candidates. So these are basically your hypotheses. Obviously, only one of these molecular formulas can be true, but we start with one and we take it as an hypothesis. This is the correct molecular formula for our for our fragmentation spectrum. And given that, we now try to annotate all the other fragment peaks in the spectrum. And we do it in a way that for each fragment mass, we can again just compute all possible molecular formulas, but we kind of say that these molecular formulas have to be sub-formulas of your precursor, because if you start with a precursor to a fragment, you'll just lose some elements, so it needs to be some part, some sub-formula of that, basically. So that's basically this restriction. But what you see here is for each fragment peak, we now have, again, some candidates of molecular formulas. And now we want to find the best explanation with molecular formulas for the fragmentation spectrum. And the way we do it is we build this graph where you connect molecular formulas via edges if one molecular formula is a subformula. So these are hypothetical losses which could be present in your fragmentation spectrum. And then we find the best explanation so that every fragment is only explained by one molecular formula. This is some optimization problem. So we have an elaborate scoring behind it. We score mass deviations. If we see common losses in the data, we score this. And basically, we find the best explanation for the data so that each fragment is only explained once. And so this is now our fragmentation tree, and this gets a score. And we do this for each of the precursor molecular formula candidates. And now each of these fragmentation trees has a score, so we can just rank them. And the highest scoring fragmentation tree also corresponds to the most likely molecular formula explanation. So in this way, we annotate molecular formula, but not maybe even more importantly, but also very important, we now have this fragmentation tree as a structured representation of the spectrum. And this is super important for subsequent steps of the machine learning we are now going to do, because all of the structure annotation steps are based on machine learning. And you can say machine learning is very bad at seeing structures in a list of numbers. I mean, spectra are just this, a list of numbers with measurement errors. So if you measure a compound today and tomorrow, you will always have measurement errors. You don't have the exact mass of the molecular formula. So by providing the spectrum in a much structured way with the fragmentation tree, we make it a machine learning much easier than also to do a good job and do good predictions for your structure. When we are then going to use the software, basically this is the panel you're looking at if you want to annotate molecular formulas, but I will then guide you through this in the hands-on. So next step, now we have the molecular formula, and we want to find out what's the structure, the molecular structure of the compound. And this we are doing with CSI finger ID. So here, there's basically one fundamental question. If you want to search a spectrum in a structure database, you need to decide how you can compare a spectrum to a structure, because one is just a list of numbers and the other is basically a graph, you can say. And there are many tools out there which go this way, that you start from a structure, you simulate a spectrum, and then you compare your simulated spectrum against your measured spectrum, because it kind of feels a natural way, because we know how to compare spectra. But I would argue that this is not the optimal way going, because, I mean, what's the one spectrum of a structure? I mean, there's no such thing. If you measure a structure in this lab or in this lab, the spectrum always looks different. So that's kind of an ill-posed problem. You can only simulate spectra for a structure in a certain lab with certain conditions at a day. So we are going another way. What we do is we take the spectrum and we predict the molecular fingerprint from it. So the molecular fingerprint is a representation, a vector representation, and every position in the fingerprint corresponds to some molecular property, such as a substructure. And yeah, if the substructure is contained, it should have a high probability there. If it's not, it should have a low probability. And for structures in our database, it's easy just to generate this molecular fingerprint because you know which substructures are contained or not contained. And then we just compare the predicted molecular fingerprint against the structure, the fingerprints of the structures. And in this way, we get ranking and annotate the compound with the molecular structure in the database. And this now sounds so easy, but again, this was a method which took some years of development and uses a lot of different steps in machine learning. We're using kernel methods. Nowadays, we combine it with deep neural networks. But in principle, you don't have to care about this. This is all running. These predictions are running on a web service, and they are well integrated with the Sirius front end. So you just click on a button, it does the computations, the predictions on the server, gives you the information back, and you can work with it. And so in the end, what it looks like in the Sirius GUI, this will be the tab we are working on then when we annotate molecular structures. But okay, now we can annotate compounds with molecular structures. The next natural thing we were asking is now my structure annotation correct? Because obviously this is not a perfect method. Some of the annotations will be correct, some of them will be incorrect. And if you really want to perform analysis high throughput, so take a whole data set with your 2000 features and run all through, then you want to have a method that tells you which of the compounds are correct, because in this way you can really do a high throughput experiment and focus on the meaningful results. And that's what the confidence is for. So what basically we want to have is we have here a spectrum. We do molecular structure annotation with Sirius and Sirius finger ID. So we have now our structure candidates ranked by score, and we just take the best scoring structure as our hit for the for this feature. But like I said, we not only have one feature, we have many of them. Some of them are correct, some of them are incorrect, and we don't know which. So we need to have some kind of score which differentiates now the correct and the incorrect hits. And our CSI finger eye score, which we developed for ranking molecular structure candidates for one specific compound or feature, this was not designed to then decide if the annotation is correct. So it can, for one compound, really decide what is the best matching structure. But as soon as I matched this best scoring structure and now compared different compounds, this is not the task it was optimized for. So we needed another method which now can really tell you for your thousands compounds which of them are annotated correctly. So in the end, you just want to have a confidence where you can, or with which you can sort just from high confident annotations to low confident annotations. It's basically the idea what in proteomics everyone is doing with Q values and FDRs, just that in metabolomics, calculating FDRs is so complicated that we currently can't do it. Yeah, and that's really the thing of the confidence score. It enables you to perform high throughput experiments and find interesting things in your data set, especially if you have some hypothesis what you're looking for, because what you can do is you can create structure databases of compounds that of molecular structures that no one else has seen before, but you can still search them. And this is what we have been doing. Here, just as one example, there are a lot of details on the slide, but these are not important. In principle, what we've been doing is, with collaboration partners, we looked for novel bile acid conjugates. So, and the way we did it was they just generated 30,000 hypothetical bile acid conjugates on the computer, because the structure is quite well known how to just derive novel bile acid conjugates with the core structure and the amino acid. And most of these 30,000 bile acid conjugates, they they don't exist in nature, but now you have a database you can search in. And then we just screened a lot of samples and found again then some hits in this database. And now you have like 10,000 of features and a lot of these hits. Obviously, you can't go through all of them, but if you have a confidence score which tells you which of these annotations are probably correct, you can focus on the top ones, and that's what we did. So these are the top 12 annotations. For 3 of them, the colored ones, we could really try to look at them and see if these are the correct annotations, and 2 of them could be validated. One was likely wrong. But from all the setup, so generating the molecular structure database, running it through, that just takes some hours. And then you don't have to do 10,000 of manual experiments anymore. You just do 3 of them and you get 2 hits. I mean, that's basically, it saves you so much time. And yeah, this way it really leverages the way of searching in databases high throughput. But sometimes you even don't have an idea how your structure looks like. It's just like that you are looking for a super novel compound, and you at the moment don't have any idea how this compound may look like. And if it's not even in a database, then we can still provide you with some information by predicting compound classes. So this is now Canopus, our 4th tool. This is specifically designed for this task. It gets a molecular fingerprint and it can predict a compound class. And for that, your compound doesn't need to be known. So that's what it's doing. It gets this molecular fingerprint we predicted, and instead of searching a structure database, it predicts common classes like, is it a glycoside, is it a flavonoid, and so on. And it can do that for roughly 2,500 compound classes. They are based on the classifier ontology from David Wishart. What they basically did is they defined rules how to automatically detect from a molecular structure which compound class it belongs to. And we now can really search a spectrum and give you the compound class for that. So for that, you don't need any structure database. You can always do it. And this is really a nice thing because on the one hand, you can, if you're not interested in a specific compound, but you want just to get an idea of your data set, you can even compare it on a compound class level. So you see different conditions, and then you see, hey, this condition has more diterpenoids than the other one, or this one has more triterpenoids. And from this, you maybe can generate hypotheses why this could be the case, and you can dig deeper. Or I think this is what we are going to see still in this workshop. You can annotate networks, molecular network with compound classes, and this gives you an idea which compounds are in this network and makes it much easier to go through the data. And yeah, this is basically the view in Sirius, which then will give you all the compound classes. And there you can have a look. Okay, so basically to sum this introduction up, the first step for compound annotation is always molecular formula annotation. And yeah, we use the fragmentation trees to do so. The nice thing is at this stage, we can do the annotation completely de novo. So your compound doesn't need to be in any database because we just de novo just generate all possible molecular formulas, and you can really find novel molecular formulas you haven't seen in any database before. And also the fragmentation tree gives you really a structured information of your data, and this is really important for the machine learning to predict the molecular fingerprint. So this molecular fingerprint is really a central core part of what we are doing in the structure analysis. On the one hand, it already describes the presence and absence of substructures, so this is already useful information to you. But because it's several thousands of these molecular properties in the fingerprint, you usually don't look at it in detail. It's rather used on one hand either to search in a structure database, and then if you get a hit in the database, we also give you a confidence, which is more used for automating your high throughput analysis, not so much for manual interpretation. And if you don't have any good hit in the structure database, we can still provide you with compound classes. Yeah. So that's so much for the introduction. So now you have a feeling of what we can in principle do. And to get a better feeling what it really means and to give you a better understanding, I would now love to have with you and basically this hands-on introduction to the Sirius software. And I need to get the right slides on the right monitor, because this, don't need this now. So the way I designed it is in the slides, in the Google Drive, in the slides folder, I also have the slides for the hands-on. And there are many of the steps in here already described what we are going to do. Not everything, but most of it. So it probably makes not sense to switch back and forth all the time, but I leave it open and you can have a look. So at some point you don't know what to do. You always have the slides just to go back and get an idea what the next step was. But first we start here. So you now hopefully have downloaded Sirius. So is it working for everyone? Someone not downloaded yet? Perfect. Also, before we start with the hands-on, maybe one important thing to talk about first is what data do you need, what to input? And I'm not talking about input formats, but really, if you're designing an experiment and you know that you want to perform untargeted metabolomics, untargeted structure elucidation, then also the way you measure your data should match that you want to do this. And just maybe this is obvious for you, but not kind of, the whole screen, right? Maybe this is obvious for you, but just do it that way. There are some important things to consider. Basically, obviously, we need MS data to perform the structure annotation. But there, the first thing starts. Sometimes people ask, what is the best collision energy to measure my compounds? And the answer is basically all of them. So I know it takes time, but the thing is, the more fragments in the spectrum, the better. So if you have like a ramped option or anything, just go for that. So we don't need different collision energies really as separate files, but the idea is just the more fragments you have in your spectrum, the more information the computational methods have to do a good job. So this is always important. If there's no fragments in your data, no method on the world can give you a good annotation. Also, then the thing about DIA measurements or MSE. So Sirius is designed to annotate a single compound at a time. So we need a clean spectrum of this compound. This is what Sirius is expecting, that all the fragment peaks in the spectrum are just from one compound. If you're now providing DIA data where you have multiple precursors fragmented at the same time, then you have fragments of multiple of your compounds in there, and this will screw up all the analysis because it's just a wrong assumption. The method thinks now all the fragments are from the same compound, but it's not true. So you get no reasonable results. So try to optimize in a way that really each fragmentation spectrum also corresponds only to one compound. And the same for isotopes, for isotope peaks in the MS. Usually you should have either just fragment the monoisotopic peak. I think that's the default way. In principle, the method can also deal with having isotopes in the spectrum, but then having all the isotopes basically in there. So because if you think of the filter of your instrument, usually it's not like a nice shaped box, but usually it's more like a Gaussian thing. And if you try to now isolate this one compound, and you also get some of the isotope peaks in there, you don't get them like 100%, you get like 50% of them, and then it distorts all the isotope pattern, and this gives weird data basically for where it's hard to get back to what's really in there. So I would say the default is just use the monoisotopic peak and you're good to go with that. Oh no, it looks better again. So this is how the graphical user interface more or less looks to you. Sirius is not only about the graphical user interface, but today we only will look at the graphical user interface. We also have a command line tool, but this is not so nice for hands-on, but it's great for running computations on a server. Yeah, you have on the left-hand side, you have just your file import, where you can import whole project spaces, MZML, MGF data. In the middle, you have like the part where you can start computations or introduce new structure databases, and on the right, you have some settings and log. And now I would say it's optional, but if you have just a file lying around, an MGF file, MZML file lying around, I need to move this on my computer that I know what I'm doing. Then you can basically just try to start your first analysis by just using one or two of this MZML. So, and the simplest way to get them into Sirius is just drag and drop them here into this part, and then it will ask you, do you want to align the two MZML files? And then you say yes, and then it will just import. So this just gives you an idea how we can start basically just from MZML. And in principle, Sirius can perform on its own all the feature detection to give you then the compound list to work with. So this is a parameter-free approach, and it's a swift way of really starting, getting your MZML in here, and start with your analysis. This is not what we are going today then to analyze, because today we will use then the MGF produced by MCMine, because there the nice thing is basically if you want to tweak your pre-processing, you can use MCMine for that, because there you can adjust all the parameters, have more detailed look at your data, how it's aligning and everything. This can be done in MCMine. Sirius is not about giving you all these features for pre-processing. We have a swift way of getting your data in if you want to just start, but basically if you want to optimize your pre-processing, this is done in MCMine. But yeah, so this is how the data looks like. If you don't drag and drop, you can also then basically use the import. And here we have then on the left-hand side, we have all of our compounds in here. So we have some data. We have some isotopes in the MS1. We have the MS data. And if you import an MZML, we also have this tab here where it gives us some information about the feature in the chromatogram. Maybe a nicer one here, where we provide you with, these are basically the isotope peaks, some adducts, and some quality stats if this is a good compound, basically. Do we have sufficient fragments in the MS2? Do we have sufficient isotope peaks to do some good analysis? Do we annotate the adduct because we see some other precursor peaks that match basically an adduct of this feature. So this is an idea that you see, was this a good feature? And yeah, what we can do besides that, we have if you want to do anything like computing a specific compound, deleting it, or order the list in some way, we have a right-click menu where you do this. It's zoom, what? You can, that is easy. You can all just do that. Yeah, it's much better. Maybe like just like that. Okay, perfect. Yeah, so basically this is the way you can start your analysis just with the MZML data. But like I said, today we want to analyze the data from MZMine, which we got. So what we just do is we start a new project here. You can see always maybe you can always see the file location of your project space. If you just start Sirius, it's in the temp directory. And now we just create a new project space somewhere. New project space. And then it starts empty again. And if you want to analyze now the MTF data, you can also either just open it with the import button or just drag and drop it here. And I'm using now this export Sirius not merged from the drive. And it just imports everything in here. Assume we now have the imported files. Basically, here we start. We have some, yeah. More MS2 more MS2 spectra in the MGF export. Yeah, so I mean, there's what the thing that you can when you export from MZMine, you can decide if all the MS2 should be merged into a single file or to keep them separate. If this is maybe the thing you're referring to, because I think they are merged by default. And in this case, I just have all of them still in the MGF. So just to show you basically that this can be done. So this is your data. You have the MS1, which is in principle should be correlated peaks. So usually it's like having the isotope peaks and the isotope peaks of an adduct. And I don't know, sometimes probably if they are not correlating well, then it takes the whole MS1. That's why I think sometimes if you don't have any correlating features in your data, then you get just the full MS1 in here from MZMine. And then you have your MS2 data, and sometimes you have multiple MS2, and they can be either merged by MZMine already, or you get all your MS2 into Sirius, and then Sirius performs the merging, and then you can still have a look how the different MS2 look. And if you want to compute something, just a single compound, you can start here. And so we can now have a look at all the parameters, what they do, and what we should take, basically keep in mind when setting the parameters. So this is now the compute panel. You have the different steps: molecular formula annotation via Sirius, molecular fingerprint prediction via CSI finger ID, searching a structure database via CSI finger ID, and perform compound class prediction with Canopus. And yeah, we start with, we want to annotate a molecular formula. So we activate this method. And now we have some parameters here, and I guide you through this. In here, the first ones are general parameters. So in principle, if you don't have any specific need to optimize the parameters, you can usually keep them as is. Like you can decide which instrument you're using, which mainly changes the mass deviation we are expecting. So like 10 ppm for a QTOF. And then we can either, if we annotate molecular formulas, we first generate all possible molecular formula candidates. And basically, we can do a two-step approach where we first score the molecular formula candidates via the MS1, so via the isotope pattern, and then already throw away all the molecular formulas that don't match well. And then for the computational more expensive part of analyzing the MS spectrum with the fragmentation trees, then we don't need to consider these molecular formula candidates anymore that don't have a well-matching isotope pattern. So basically, if you have good isotope patterns in your data, you can keep this as is. But if you realize that often already the +1 or 2 peaks are missing from your isotope pattern because you have very low intense features, then probably don't activate it, because if your reference isotope pattern is not that well, then it may basically also throw away your correct molecular formula. Yeah, we have some mass accuracies. Here, basically a parameter. If we see isotope peaks in our MS, how should we deal with them? Usually in this data, we don't see any isotope peaks in here, so this is not so important, but we can either ignore them or score them. And then these two parameters just say how many of the molecular formula candidates I want to store in the end. So we will compute all of them, but we only store the top 10. And for each ionization, we also want to store one. If you don't want to go de novo, but search in a database, you can do that by just clicking on a database. We provide a bunch of different ones. So basically, Biodatabase is our big default selection of databases with molecular structures of biological interest. So this contains basically Biozentrum, Capi, Coconut, and HMDB, and a bunch of other databases which are in here. But we also have like PubChem included, which contains 100 million molecular structures and I don't know, a million or 2 million of molecular formulas. But we want to go de novo, so we don't click on anything here. Then we can decide for the ionizations to check. So currently in Sirius 5, we still have the concept that for molecular formula annotation, we basically consider the ionization without any adduct. So like M+H, we have at this stage, and if you think it was a water loss, we only consider this for searching in a structure database, because the spectrum, if you annotate molecular formula, we cannot really, from the MS2, decide if this was a water loss, in-source loss from your precursors, because this is the information in the MS1. That's why if we want to annotate a precursor molecular formula, at this stage, we only decide if it's a protonation or it's sodium, but not there was a water loss in there. Yeah, these parameters are basically just optimizing fragmentation tree computation. So how long shall we do it until we basically stop? If it's a too large compound with 10,000s of molecular formula candidates, it can take some time to compute fragmentation trees. We can set a timeout, but in general, or we only heuristically compute these. Usually you don't need to change these parameters. And then here's a set of the elements that you expect in your data set. So basically, these are all the elements we use for generating molecular formulas. And some of these elements we can auto-detect. there's elements which you can just guess from the isotope pattern. Like, is there a sulfur in there? Is there a bromine in there? So if you see here, if you click auto detect, it detects that it expects 0 to sulfur in there. But for the default ones, CHN, OPS, we just consider them normally. And yeah, these are basically all the parameters for molecular formula annotation. Then we just say we want to predict the molecular fingerprint. Like I said, if you also think there may be some adducts in here, you can set them. But I think we are good to go. And then we search in some database, here the biodatabase, and we may even compute compound classes here. And wait, no. Now that you selected everything, if you want to run it at some cluster or at some point, you need to use the command line tool. But the nice thing is, we can generate you the command for that, basically. We don't use it now, but in principle, if you don't want to set all the commands in the parameters in the command line tool, but you are more familiar with the graphic user interface, you can just click through it and get the command and copy paste it, and you're good to go. Yeah, but in principle, we just do the computations, and then this is how the results look. We have for this part, already in the data was detected that it is some ammonium adduct. So basically what we provide in the graphical user interface are only the fallbacks if it's not auto-detected. And you can see here the that's not a nice example because there are so many things in here. Just maybe we compute a nicer one here. Something with where we don't have all these peaks in the presumably isotope pattern. So here, what we see, we have molecular formulas, and they were ranked by score. You have also now you can basically compare here your isotope scores, which are very bad for this compound. So the MS1 information is this one. You have your isotope score, which says how does the simulated isotope pattern match the measured one. And it seems to be that all of them are very off. You see here that the simulated isotope pattern here on the top, on the bottom doesn't match really well with the measured ones for all of compounds. So maybe there's either some rare element in there or something was wrongly combined with the isotope peaks here. Yeah, it's so that would be then the one that it's here. Yeah, maybe that's why I remember from the slides to make it so DOM sample is basically the hardest thing you can use for annotation. And maybe, I mean, that's also the very early compounds, right? Before 1 minute, maybe this is not the best example. So I remember what I wanted to do is basically at least if you now have like 5,000 compounds in your data, I start maybe filtering by clicking here and provide some reasonable ranges for retention time and mass. So let's say we only focus on compounds with a mass of 200 to 600 and starting at a retention time of 2 minutes to 10 minutes. So then we should get rid of all the strange stuff in the beginning of the end of the column. And maybe we make it even more easy to ourselves and use only the features where MC Mine already annotated the feature with an adduct. So these should be in principle the better ones, because if you see a second feature and can from this judge the adduct, hopefully these are the better quality features in your data set. So basically you can just apply this, and then we now end up with these 88 features here, and can do the thing again. And I think now we will have some nicer feature here for computation. So we start molecular formula annotation, detect the adducts, do fingerprint prediction, structured database search, Canopus. Compute. I think these are the ones I rather had in mind. Yeah. So you have it in your also. This is the one is in the slides basically, so that we don't have to. I mean, you don't also have to have the exact same filter in here. It's not so important for the hands-on, but in the slides, I think I use these parameters here, and then it gives you an idea. Yeah. This was arbitrary. Yeah. In principle, maybe. So maybe one note to this parameter. This is basically the main thing. What it does is set the assumed mass deviation and some minor changes besides that. And I think we assume like QTOF 10 ppm, Orbitrap 5 ppm. So if you don't know so much about the data and just be on the safe side, you can also always just use the QTOF parameter. Yeah. But it's Orbitrap data. Yeah, that's the thing. So QTOF parameters are in this way a little bit more loose, I think like 10 ppm. And so this is usually the default. It's just if you know you have really some better mass deviation, you can go for this parameter. It usually just makes it a little bit faster, but not so much changes in here. So this is something usually just not so important. If you like know you have really good mass deviations, low mass errors, then you can with the FTICR you can use it, but it also doesn't break the method. If you just do this, you just will get more molecular formula candidates with higher mass deviations in there. Yeah. So okay, now it looks much nicer, and yeah. Yeah, so basically that's why I was looking for such a feature, because now we have some better scores in here. Because for the first one, basically here were all zeros in there. Here now you can see it a little bit better. Now we have all of our molecular formula candidates. And here in the MS1 mirror plot, you can see how the different simulated isotope patterns change. And based on these changed isotope patterns, we also have a score here for the isotope peaks. And it's not like I can say that a score above a certain threshold is always a good isotope pattern, but usually if you like have an isotope score above 4, it's quite okay, but you should get a feeling for your data basically. Here you can see a highlighting always in relation to the other candidates. So that basically based on only the isotope pattern, this is the best matching molecular formula. But if we consider also the MS2, the total score is better for that, because now we go, so isotope score is MS1 only score. Now we also have the MS2 information in here. So this is our MS2 spectrum. And for that, we now computed these fragmentation trees for each molecular formula. Based on the resolution, you can't see it that well here. My zooming with the touchpad doesn't work that well. You know. This basically now annotated the spectrum with fragments. And yeah, this has a specific score. The fragmentation tree score is this here. So the highest scoring fragmentation tree was for this molecular formula. And to now get the best molecular formula in total, we just sum this isotope score and this tree score together as a Sirius score, and it's just ranked by the score. And this you can see basically here, just that because these scores, they don't have a fixed range. Like if you have many fragments in your data, in general, the fragmentation tree score will be higher. So it's not like always a score above 50 is good. You can see here, I mean, you have different molecular formulas, and both of them have a score above 50, but obviously only one can be correct. They just have this high score because there are many fragments in there, and there seems to be some good explanation that both can explain some fragments in there. So it's hard to get absolute values, so we try to transform it into a probability. And this is what you see here. What we do here is we have the sum of both of these columns here, but then we transform the score in a way that all of the numbers here add to 100%. It usually is a bit too optimistic for the molecular formula hit, but it gives you an idea. If the score is like 99.9%, it's usually much too optimistic. It's never this higher chance of being correct. But if it has a 0, it's usually not a good molecular formula hit. That's the way we rank, but we also have some more additional scores that help you to judge if this is a good spectrum, if this is a good hit. And this is explained peaks. It basically tells you how many of the peaks in my MS2 spectrum were explained by fragments of the fragmentation tree. And you can see here 38 of all the peaks were explained. For this molecular formula, only 19. So you see in the spectrum also highlighted, the green peaks are the ones that were explained, and there seem to be many peaks with this molecular formula that cannot be explained, which can be either that this is the wrong molecular formula, or that there are just some peaks in the MSM spectrum which came from a different compound, and that's why you can't explain this peak with this precursor molecular formula. So this is always the thing you need to judge on the data to sanity check. Yeah, the same is then total explained intensity is the same as explained peaks, just for summing up the intensity, how much intensity is explained, and then also what's the medium mass error of your molecular formulas of the fragments and your medium absolute mass error. So with the one, with this one, you see basically, is there a shift in your annotations, the systematic, if this is very high or very low, and if you look at the absolute values, you see is it a broad range of mass errors. Yeah, you can also see this in detail then for the basically also in the fragmentation tree. If you look at the different fragments here, you can see relative intensity, the score, and also some deviation of each of the peaks. Yes, so I think that's about it for the important part for MS1 information. Maybe, yeah. So here you have the Zodiac score, where you don't have any numbers. This is basically the idea. If you run computations on your whole data set, then it looks like that. And what changes in here is you have now another method in here called Zodiac, which is basically an addition to molecular formula annotation with Sirius. So Sirius performs molecular formula annotation for one feature separately, and it has a good annotation rate for molecular formulas, but still it's not perfect. So we decided to develop Zodiac, which then basically optimize molecular formula annotations on the whole data set. So it just takes all the molecular formulas from the Sirius step and re-ranks them for the compounds based on the idea that your data set contains a lot of compounds that are kind of related to each other, because you have some biotransformations in there. So you have related compounds in there, and you can make use of that to optimize your annotations and improve them. If you see basically for one specific molecular formula, I see a lot of biotransformations in my data set, I should rank them higher. So that's basically, if you run this, it gives you a little bit improved molecular formula annotation rate, but you have to perform it on the whole data set. And so we won't do this today. We want rather to look now at the structures. I think most of you are in the end just interested in how can I annotate my molecular structure with Sirius. And this is what now these I think IDs for. So we annotated the molecular formula, and with this we have a fragmentation tree. From this we can predict the molecular fingerprint. This is this one here. Here are basically all the molecular properties predicted by the fingerprint with probabilities. And you can see what is predicted to be present here in green, or as a feature, just to give you an idea, or what should not be in there in red. So you can see the substructures. This is something you usually don't look at, but this is the whole fingerprint we predict. And we predict one of these molecular fingerprints for each fragmentation tree, so for each different molecular formula here. And then we search them in the structure database, and this is now the result. Here in green, this is the best scoring molecular structure hit for your compound. And you can see, first of all, for this compound, we have the different sources where we found it. Like it's contained in Cabby, in Biostruc. And you can even click on Cabby, and then it will guide you to the website. It just automatically opens it, and then you can yeah, so basically these are the sources that you can open. Like you can open your compound in PubChem, which usually has a lot of different 2D structures in there, but you can also use Biostruc Cabby and so on. The gray ones are basically some sources, some specific sources which we provide to search in. But so basically you can select them here in your list. But you can't click on it and link it to the database, because either we don't provide it or they don't have the feature to search for an ID, so we can kind of automatically open it. And the yellow one are custom structure databases, the thing we are going to talk next about. So this is basically a database you can specifically create and search in. This is the yellow ones. Then we have like a structure representation of your molecular properties here of the fingerprint. These are these boxes here. So they look now first a little bit funny. So, but they help you to get an idea what molecular properties are predicted. So basically, to give you the idea what that means, we even have some slides, because it was always hard to explain. So I just use this. So basically, this is your molecular structure candidate, and it has a fingerprint. So, and all the black boxes are properties that should be contained. All the white ones should not be contained in your structure, or are not contained. And we also, from the data, we predict such a fingerprint. And the way we visualize now how these match is we take all the properties that are here contained in your structure candidate, so all the black boxes, and also use them from the predicted fingerprint. And the colors mean basically, if it's blue, then we predict it to be present. If it's red, we don't predict it to be present. So basically red is a contradiction to your candidate. So we It should be basically in your structure hit. The box says it should be contained in your structure. And if we then predict it to be red, then we say, no, that's a contradiction. We predict it not to be present in here. If it's blue, we say also, yes, it should be in there. And then we have the different sizes of the boxes basically just tell you how good is our prediction. So how good is the machine learning predictor to do this task. So it's maybe easy to predict an H2O, but maybe very complicated to predict a specific fluorine substructure. I don't know. And that basically gives you an idea. If it's a big blue box is good, a big red box is bad, and the small ones just the predictors are not that powerful. And that's basically what you see here. So you can just play around with it to get an idea what should be in there or not. Here for the candidate, for example, this is a substructure we predict not to be present, but it's in this molecular structure in here. You can also just overlay all of them, and then you see that this is basically a very bad match to our predicted fingerprint. This is just for visualization. So this is more to give you an idea if this match was good. The method just ranked by score. So there is a Bayesian network scoring behind it, which basically does the job in the best way to take one fingerprint and take the predicted fingerprint, just match them and give you a score and rank them. But this is nice if you want to then really see which parts are more certain for the structure and which are not. So that can be helpful in this way. And what else? Okay. So yeah. So yeah, so the things. So yeah, the first thing, this is a log probability. So basically, the best score you can reach is 0, and then it's just negative here. And in Sirius 5, we still have this value in here. So this is basically a predicted Tanimoto from the predicted fingerprint to the molecular fingerprint of the structure candidate. But it was always a little bit misleading. So for the next version, we keep it out because we ranked by this score. This estimated Tanimoto we only included because people know the Tanimoto. So that's why this is the important one. You also get something like log P estimated from the structure if this is helpful to you. Yeah.
Zodiac subtool.
Yeah.
Is it more or less effective doing it in groups that have been like identified by GNPS versus the set of the pattern?
Just do it on the whole data set in principle. So you cannot it's also building a graph in the background basically to optimize. And this has much more connections than a human being would look like basically on yeah. So in principle, the method should decide on its own if there are good edges in there or not, because it uses a different scoring for the edges and all. Just use everything. But the important thing is use it only for biological data or data where you have, there is some biotransformation there. If it's like and independent compounds in there which have nothing in common, you shouldn't use it basically. Yeah. Okay. So basically, I think that's all about the scores. You can also filter like X log P, similarity, some even smarts matcher, or you could look for a specific database where it's contained, and then you can just filter your list to do so. We talked already about the fingerprint. Like I said, this is now the best scoring hit. We also have hits for other molecular formulas, which are just worse than this one in the score, which you can see in the next tab, basically, where we put all of them together. So here you can find now all your hits also for different molecular formulas, ranked by the CSI finger ID score. And this tab is for substructure annotation. So this should give you, again, some more confidence in the CSI finger ID structure hit by doing something, I'd say, similar to if you know metric for annotating fragment peaks in the spectrum. So what we do is we take the molecule and fragment it into pieces and try to explain the fragment peaks in here. And with this, you can basically just judge if your structure hit makes sense. This is not used for ranking the structures. So basically, these, I think I already decided in which order they should be. This is really for manual investigation, more to give you an idea. For example, for this, we have now some high peaks here, and they can be explained by some fragments here of your, so some substructures of your whole structure. These are the high peaks, the purple ones. But then here, the green ones down below here, these are all annotated with molecular formulas, but we cannot find any substructure in here that explains them. So in principle, you want to have like a spectrum which is all purple with all the peaks explained by substructures, but obviously this cannot always work because if there are like rearrangements in the structure, we cannot assign them to a peak because we only try to find substructures. If we can cut it into pieces and assign it to a peak, we can do that, but we don't consider rearrangements. So if the spectrum is basically all black or all green, it means we cannot assign peaks with substructures in here for this hit. If it's all purple, we annotated them. And yeah, so this is mainly meant as a sanity check for that. And the last thing is we can compute compound classes. And this is this panel. So here we predicted the compound classes for this compound, given that this molecular formula is the correct one, because this prediction is based on the fingerprint. We have a predicted fingerprint for each molecular formula. So always the molecular formula is really important that this is correct, that we can also get reasonable predictions here. And yeah, if you don't have any idea of the structure, we can give you basically these different levels here of annotation, like it's a polyethylene glycosol or ethers, or it's just an organic compound to be very, very unspecific. So this is kind of an ontology, the classifier ontology. So it gives you kind of a main class, but also then all the other ideas. And if you don't know what it is, you can just click on it, because I'm not a chemist. I usually don't know what this means, what's standing there. And then you are linked to the classifier website, and it gives you some idea of how a compound should look like if it is part of this class. So that's very nice. Yeah, and in principle, like I mentioned before, these are roughly 2,500 classes in here that we predict. So a lot of them for one specific compound. Obviously, this is only part of some of these classes. So these are the ones we predicted with high probability. And yeah, so you can also see some description what it means. That's it. Are there some, at this moment, some general questions about its method? Is something completely unclear still so far? So, okay, which yeah.
So I input my compound to the GNPS library. So I input the whole of the metabolites there, but I cannot find anything in GNPS, which is I've already put some of my standard compounds or synthetic standard compound to the GNPS library.
So you're asking about this structure database?
Yeah.
So basically,
yeah.
I mean, this is not a live clone of the GNPS database. So at some point we downloaded basically GNPS spectra. So also, I mean, just the reference spectra, and use this spectra to add them to our structure. So use the compounds of the spectra to add them to our database, because then if you have a match in there, you can link to a GNPS. That's why we did it. But this is not always up to date. That's kind of, there will be a lot of reference spectra in GNPS that are not contained in this structure database, because every now and then we import it and then we update it, and then just, it's usually not a specific database to search in. It's more like, hey, if we find a structure that also has a reference spectrum in GNPS and we can link to it, that's nice for you to have. So that's why it's in there more.
Thank you. Also, in this window, if you declick tag lipids, then you will not get any lipids family compound in the, right?
This basically, in the next version, we basically just, of starting first. The idea is we can annotate lipids just saying it's a lipid class, because usually for a lipid, you may not have this structure in the structure database because there are so many versions of it. If you have a long aliphatic chain there are so many different versions, you can't have all of them in the structure database. And it makes usually no sense to search them with CSI finger ID in the structure database. So we want to give you an idea and just flag, oh, I think this feature is a lipid. So probably don't trust the structure search so much, or at least we already annotated as a lipid, you know what it is. And this basically just allows you to either activate it or deactivate this way. So it still performs the normal structure database search, but we will also have a look at how this looks if you have lipids in there. But in general, there's no good reason not to flag it because you still perform the rest of the analysis with it. Maybe one thing I missed, I have it on my hands-on slides, but because of the back and forth, I just missed it. One important point before you ever just start analyzing your data and you got an input file, it's always good to have a look at your input file. I just want to remind you that the data you put into Sirius that are just text files, so an MTF file you get from MZMine is just a text file that you can open with an editor. And this is important. I mean, you don't have to do it every time, but sometimes it may be that you import data to Sirius and then no features in there, and you're wondering, hey, why is my feature list empty? And the first thing you should always do is have a look at your text file, because it tells you, is there even a feature in there? Is there MS2 data in there? That's maybe the more important thing. Sometimes people try to basically input a file where only MS1 information is in there. So it's always good to have a look and read just the file. It's basically easy to see that it has a feature ID, it has a level, MS1 level, MS1 or MS2, and PEP mass and charge. So if you scroll down a little bit, you also will find then some of the, basically search rather, MS level. You will find that you have your data with MS level 2 in there, and all looks good. If it has annotation with a charge or sometimes with an adduct, all this information you can find in here, and this is usually a good thing you should check. The same also with MZML files. You can see, you can open it, it's just XML. You can open it and see what's the isolation window and what's reasonable data in there. Just before you wonder why something went wrong, it's always a good idea to do that. Yes, so far so good. So basically here we just now looked at one individual compound. But now assume we now want to analyze the whole data set and want to get some meaningful results from it without looking at all of these 5,000 compounds. So this is now the next step where I prepared also something. Was another one? Oh.
Just my question. When you compute everything and then go to structure, you have the yellow database
Yeah.
And I don't know, like, I don't have it. And the question is why?
So yeah, this is now the one we are doing next. This is a custom database I specifically imported. So we just can go this way. Everyone can now just try to import their own custom database. So this is the one we are doing next for analyzing the whole data. And we do it by clicking on the database, right? And then what I did, because I honestly have no chemical background and so no big idea of what's interesting compounds in here, what I did is I just went to the paper and looked first what are the compounds that were annotated there. So this is basically this one here. And then I picked another one, which of the compounds that were annotated, and asked the question, what if we cannot find this in the data? Can we find biotransformations of it in the data? So these are basically the two questions I wanted to tackle. And for that, we can use custom databases. So if you have an idea what you're looking for, you can always create databases with your own molecular structures based on some smiles. And this is in the drive. We have, if you have seen this already, here in Sirius, we have now these two files, custom structure databases, and this is basically the ones where I included it. If you open it with a text editor or some Excel, you see it's basically just the smiles with some name in there, or for the other database, it's even just the smiles. And maybe we'll need this in a second. So, but in the way you import it, there are the two files, and you just basically add a database by clicking here. Then you specify a location here, click through in a directory, and then you can just drag and drop the file in here. Maybe just do another. Just B4, I don't know. And then if I have do I have the file in this folder? It's basically if you just drag it, drop it in here, it should start, or you can also copy paste smiles in here and it creates your new database. So you can try this, and in the meantime, first question, how did I create this custom database? So first, the paper database where we are the smiles of the 6 structure in the database. This one here is one of the structures. And what I just did is, I want to have biotransformation. So I go to PubChem. I search the smiles. I just copy pasted it. I hope this is the first one. That's the correct one. Yeah, it's that. So assume this one you're interested in. You currently don't know if it's in your data set. But hey, PubChem has this nice part here where you just look for transformations, and you have like 20-ish compounds known to be transformation products of this one. So you go to each of them, just copy the smiles in a file, you're done, and now you have a custom database. Or you can use some other tool like Biotransformer from the David Wishart lab. It's also a way of predicting biotransformations given a compound. I won't go into detail with this, but there are tools out there which generate these hypotheses of potential transformation products. So they don't need to exist, but you can generate the idea that it may exist, and then you can search for it, basically. And with this done, with our custom database.
Marcus,
Yeah?
I have a question.
Yeah.
I normally, from my students and people that I collaborate, I have always the question with Sirius that let's imagine that you have the MS1s for a specific compound and all the MS2s for the top 5 in one specific retention time. So you have all these lists and you sort it or filter by retention time. And can you work with all these features, work at the same time and get a better result for the annotation? Or it's independently done for each feature and the annotation is made for each feature?
So if you have different features in a list, this is completely independent, except for the except for Zodiac, basically optimizing molecular formulas but for all the other steps, it's really one feature in the list is independent of each other feature in the list. So
Sirius doesn't integrate all these features in order to get better results for the
So if you're basically referring to, if you have like 5 different features in here, then yes, not. So these are, where's my cursor? So this is independent of this and of this, yeah. So these are all completely independent of each other, yeah. Okay, so basically now you may have your custom database. If it didn't work, it's also not an issue, but yeah. Yeah. It's maybe it's also on the slides. You can have a look if it's not working. It just click here on the add button, specify a location first, and then drag and drop the files here, or just copy paste smiles in this window. Then okay, maybe it could be if there's not we first need to specify the location. Maybe there's because it's just started, I just also realized we have an updated version of this import in a new version, but for this Sirius 5, I assume because it just starts when drag and drop into and you haven't specified the location, I think that maybe produce an error. So first specify the location here and then try to drag and drop it afterwards because it just starts import, which is maybe a little bit unfortunate. So, but even if it didn't work, it's also not so big of a problem because now we can just start with, we can just use the project space I provided. So because it takes some time to compute everything, I have a project space as a zip, which I provided you in the drive, which is similarly named to this one, I assume. This is the 600 MB zip file. You first need to extract it. If this took too long, you can also use the smaller one, which we then use after filtering. But in principle, you either go to open at the top there, or you just drag and drop it in there. And then it just opens. And you see that it's not so that the data doesn't become too large. I already filtered for all after annotating the compounds, I filtered for all the structures that have a confidence above 0.4. And so instead of the 5,000 features, we end up with 636. And what we now wanted to do is basically search in a custom database. So we already did this, or I already did it for you. You can basically rerun the same thing on your MGF data by running Sirius, running fingerprint prediction, searching in a database, selecting next to bio also the custom databases, this one and the paper database, and just basically run it. I think the only thing I changed from the default parameters was if MZMine didn't annotate the adduct, because this is unknown, then we need to decide for one. And I think I've seen based on the data that there are many sodium adducts and ammonium adducts. So I think ammonium and sodium I added to this list of adducts that are used if I don't detect it by the MS1 data. But based on that, the rest should be all default parameters. You could rerun it or just look at the data I pre-computed. And now you want to see only the features that we found in our custom database. So what we do is we filter again, and now we go to our menu here where we search in the structure database. And this is the one with the biotransformations. And the other one was called paper database. And let's say I want to have a hit at least in the top 3 of my structure candidate list. And if I do that, it filters. And now these are all the remaining features where I have a hit in a custom database. So I think here these ones have also been found in the paper. But the ones we want to focus on is basically this one. I think is the original compound structure that was also found for the paper. But assume this is not measured because you only see the biotransformations. You don't see it for some reason. I don't know. Maybe nothing in the end after all your setup remains for this compound. Then we want to have a way to find the biotransformations, and we did this exactly with our custom structure database. And this is one of these presumably transformations of your compound. And really the nice thing is, if you now look at the sources, this transformation product here, this is, first of all, you don't have any reference measurement for that. It's just in no spectral library. It's even not in some of the bigger structure databases. It's not in CAPI, it's not in HMDB, it's not in KEC. But we produced a custom database to search it, and we still find it here. It obviously is contained PubChem because we got it from there. But usually, if you search your structure in a database, we search in this biodatabase of biological interest with 500,000 of structures in there, I think, because searching PubChem is really super difficult and performance goes down. So usually you search in these 500,000 structures to get reasonable hits for your biological data set, and you search in PubChem only as a fallback. But yeah, so we have a nice hit. We can now also look at the predictions here a little bit. Does it make sense? So is it a good hit, basically, we want to know. We can highlight the substructure and see what matches or not, and try to make some sense. Based on the confidence score, it is a very good hit. But now for the automated method, to filter it, this is a good way, but you still should manually check why this may be a good hit. Because the confidence score is a machine learning score, just machine learning product, and it has some input features like what's the score of my compound and what's the score difference to the second best. So usually it has a very high confidence. For example, if we have a very good hit at top position and then we only have bad hits, so this will boost the confidence score, for example. And that's maybe because the first compound is really the first structure is really the correct one, but it may also be that we just have strange hits in our database. So it's always good to check this and to see now, does it make sense, the whole structure annotation? Because if you look now at, for example, here, the substructure annotation, you see how the peaks may be explained. But there are also many peaks that can't be explained at all here. So you now have to make the decision if this is reasonable. Because, for example, what I found here, if I really look at how to explain the fragments with the fragmentation tree, you can do all of that. And you see here, you have like molecular formulas that may match the structure of your core part that may help you with interpreting that this is really part of your hit. You also, I think you even see it in the predicted fingerprint in here. If you filter, we also predict that this core structure should be in there. But if you really want to be certain, it's always nice to manually check also the spectrum. And honestly, I also see some strange part in here. Yeah, a lot of here's this very strange fragment explained this very strange loss here. And I don't know if this makes sense, or if it's an artifact because there are some low intensity peaks here which can't be explained in a different way. Maybe it's not a super clean spectrum. That could be another explanation because we have basically we have some many small peaks in here which can't be explained else by molecular formulas. And I think these are the ones here now we are trying to explain in the second part of the fragmentation tree. But interestingly, for example, if you have some time to look into this, so for me, this loss seems strange, but if we look at our main structure we are interested in, seems to be that also this one is producing something like that in here. So there are some similarities in here that also this loss of a lot of nitrogen without or with only one carbon is adding. So this is basically now biochemistry knowledge you can maybe infer here or use to make sense of the data. Maybe there are also just some rearrangements that produce this. Maybe that makes completely sense because these tails here are doing something. I don't know. So this is basically just an idea of how to look at the data, and now you can use your expert knowledge to make sense of it, or say in the end, this is not a correct annotation. For that, we have all these ways to leverage basically this knowledge. Yeah. I think I also highlighted it in the slides if you want to have another look afterwards. I think I highlighted all these compounds. Maybe one thing, yes. You also can check for a compound is was the adduct annotation correct? Because all these molecular structure annotations always depend on the correct adduct being used. So you could even, if you are not certain if the correct adduct was used, even change this here and rerun it with different explanations here. So you could that was for this compound here. Right, I prepared this one hit where it makes sense, just to go to this one. Also, we have a full text search here, so it's always nice if you want to search for a specific feature. Ah, it was this one, okay, to rerun. Basically, what you can change is just trying some more adducts here to see if they make sense or not, and research in your database. And then just results change a bit. No, the filter doesn't work anymore. I have to recompute. Feature here. Yeah, and then you can also check for different adducts. Maybe one thing I haven't talked so much about so far is so the different adducts for the same precursor molecular formula are basically here. So all these molecular formulas here, they only differ by the adduct that is assumed. So on the molecular formula level, all of them will have identical score because based on the MS data, we cannot differentiate these. But if you then go to the structure database, you can see if you now with other adducts also get a hit in the database. And the good thing is this one is still our best hit, but in principle, you can, sometimes it may happen that the wrong adduct was annotated, and it's always possible to go back, also change the adduct from the pre-processing and double check if this is really a good hit, basically. So these are all the options you have to do so. Yeah. And really, you can search in other databases if you don't get a good hit. In principle, the biodatabase is the combination of mostly all the databases here except PubChem, and it's usually a really good default. But if you have the feeling in this database is no good hit, you can always search in PubChem, which is basically the biggest structure database we have. Okay. So which feed? Ah, yeah, the lipid thing we wanted to talk about. So as a final thing, I talked about lipids. So in principle, CSI ID is not good for annotating lipids because, I mean, these are these long chains that, first of all, you usually don't find them in the structure database. And so using the molecular fingerprint to score lipids or also score peptides is just not a good idea because the fingerprint only says the substructure is contained in there or not. So, for example, your peptide bond, yes, it's contained in a peptide, but it doesn't tell you how many of these bonds are in there. So it's not really a good way to use it. It's great for general small molecules, but if you go in these specific classes where you have these repetitions in there, the fingerprint won't tell you how many of these repetitions you have in there. So we have a specific tool for lipid detection. And this is called Algoro because here always it's just one click and you filter by lipid. But again, someone took some time to make a reasonable machine learning method to predict all of that. And not just a nice button. So we always have a specific name for each method, also then to present this in the publication for that. But you just need to do this. And then it should go over all your hits and find the lipids in the annotations there. And then I can show you an example where it annotated. Yeah. Yeah. If you have very big structures, like, yeah, I mean, if you assume that it's in the database, we can find it, but yeah, if it's too repetitive, it may not be the best tool to do so. If there's, for these specific tasks, if you already know it's a lipid or it's a peptide, there may be other methods that work better. Because they're only looking at this specific class to optimize, basically. And so it may also be in this case. But the usual thing is that you don't have like 100% lipids in your data set or only sugars. So it's good to have this generalist tool to first give you an idea. So that's the thing. It's usually not that we do completely wrong, because taking the lipid example here, it was predicted to be a phosphocholine. And also in the structure database, it's a phosphocholine, so we also take it that this may be something like that. But maybe it's not exactly this one, especially if we have like this double bond thing in there. I don't know. Here, I mean, yeah, it's something like this, but really we cannot differentiate. Honestly, I mean, mass spectrometry can usually not differentiate these compounds in here if the double bond is here or there. So that's the way. So either you have a tag here and it's nice, then basically also CSI finger ID found at least a very similar structure. But sometimes it may happen that the structure here, it's a lipid and probably not in a database, so we can't find it. And then it's good to have this flag, hey, it's a lipid. Rather check if this is true and not just blindly use the annotation from CSI finger ID. That's the idea. Yeah. I think we even map again, we link to lipid maps if the structure is annotated. You can give it a try. So I think, yeah, we are almost over time. So last thing you can do, so this is very specific thing, but like I said, we can also use the confidence score if you don't have an hypothesis in a custom database, you can still just sort all your compounds by confidence. And then at least the nice feature is that the first ones should be more meaningful, more often correct than the ones on the bottom. So if you spend your time somewhere for manual investigation, it makes more sense to start at the top at the probably correct hits and go down in general. Yes, I think these are most of the features here. You have some feedback or? No? That's great. Yeah.
That's actually the alarm that you
got it.
finished the top. Now,
Yeah. Maybe just
now, Marcus,
yeah. Actually, the last final. Yeah. How long does it take? Like 4 minutes? 1 hour. Yeah. That's fun. Yeah. That was fun. Yeah. I think these are the most important features. One last thing, if you want to now integrate all this information with cytoscape molecular networks, then you can just export summary files here. Again, you specify a location and it will write the summary files in there. And then you get like a TSV file with the top structure hit, the top molecular formula, the scores and everything, and the feature ID. And then I think Daniel will show you how to integrate it with Cytoscape. The thing is because the MZMine file changed in between. This is if you are now on the next day or today want to work further with it. I, in principle, already prepared it for you. You can also rerun it. So the new project. Hey, it's a very long minute, I have the feeling. So this is basically the data you have been using with MZMine. I already pre-processed it here. You can also do it yourself, but also here's the whole project space. And the exported summary files are here, where you probably will use the compound identifications for your TSV file. So this is already in a drive, and probably Daniel will then guide you through this. But this is something in Sirius, you just exported summaries here. And even, my goodness. And if you don't start with MZMine for pre-processing, but you started with Sirius and the MZML, you could also export an MGF for GPS. This is also possible. I think these are the most important things. What I missed? We have a log where you can see errors in there, especially for something is missing in my import. You can click there and see maybe something like, oh yeah, this was removed because it's multiple charged or anything. All this information can be found here if you need to dig deeper. I think in principle, that's it. Just as a teaser, I want to the last very minute. We have a Sirius 6 version, so I'm sorry, some of the things that you learned here will be some of the features we looked at here will slightly change in the new version. Or is it not in the... just not to talk too much about it. But the most important thing, obviously, a dark theme is always important for each software. But hopefully Sirius will come out in the next 3 to 4 weeks. And it will also add, on the one hand, we also kind of implement spectral library support in a way that we annotate our structure annotations with spectral hits to give you, again, another layer of confidence that you can manually check in case you have a spectrum. gives you an idea. We have, if you know MS Novelist, it's basically a way, now I have been talking about searching in a structure database. You can also generate molecular structures de novo. This is what MS Novelist is doing. And this is not a default method you should use instead of structured database search. But if there's a completely novel molecule and you want to dig deep into the data and want to get some idea what it could be, this generates you structures de novo without any database, so it can help you get an idea. So it will also be included. We change our workflow a bit, so I'm sorry if the compute panel will then look a little bit different, but also more lean and better to understand. Especially the thing with the adducts I talked about, that we first look at ionizations and then at adducts. We changed just because it seems to be more complicated. We now have then only adducts and from the beginning on. And we have scripting support. So if you want to use it with like get your data out to Python, this will be possible. And we have better also then a new confidence score and new fingerprint features. And I think I should stop here at this point. And
I think the guy who is activating the alarm got labeled and pressing enter. He's super happy doing that.
Thank you for your patience.
Thank you very much, Marcus, for such a nice talk.